Hello and welcome back. We're going to look at exponential functions again. We've talked about exponential functions before, but let's remind ourselves what they look like. So exponential functions will be mainly in the first quadrant, but they can go into the second quadrant as well. They start off, kind of innocuous, and then they just shoot up really fast like this. Well, the reason they do that is because the input value determines how many times we're multiplying by a certain multiplier. So it will start at, we often have the starting value, which I'll call 0a. That's going to be basically our y-intercept for this function. But it doesn't have to grow. It could decay as well. In fact, we could start back on the left, to the left of the y-axis. You start really high, and then it kind of levels out like that, getting ever closer to the x-axis, but never actually making it there. And again, we still have the same y-intercept, which I'm going to put right here. So what determines this? Well, the function we're going to look at, and we've talked about this before, y, the output is basically your start value times whatever your multiplier is to the power of the input. So that the input tells you how many times you're hitting that start value with the multiplier. Remember, order of operations says you do the exponent first. So you take your multiplier to a certain power and then you multiply it by your start value. In letters, in terms of variables, I'm going to call the start value a and the multiplier b and our power to the input. So y equals ab to the x. Remember, this b is not the same as the b in linear functions. The b in linear functions is the y-intercept. Here, 0a is the y-intercept. So 0a is the y-intercept. And b is our multiplier. Now, also be aware that this multiplier is related to a growth or decay rate. If you have a growth rate of a certain percent or a decay rate of a certain percent, that means it's taking the previous value and multiplying it by that multiplier that's related to that growth rate. Then that multiplier is 1 plus the growth rate, right? If it's a growth rate of, say, 20%, then your multiplier is 1 plus 20%, or 1.2. If it's a decay, then it's 1 minus the decay rate. So if it's a decay of 15%, then that means the multiplier you're multiplying each time by is 0.85, 1 minus 0.15, or 0.85. And you could wrap these two together into just one thing. It's just 1 plus the percent change, I guess you could say. And if the percent change is negative, it's a decay. If the percent change is positive, it's growth. You can combine it into that. So let's look at, well, what situation determines whether we're growing or decaying? Well, if we look at our multiplier, if we're growing, that means we're taking 1 plus our growth rate, 1 plus some positive percentage, some positive decimal there. So that means if we're growing, then our multiplier is bigger than 1. If we're decaying, then we're going to take 1 minus some decay percentage. So basically, the b value never goes below 0. It's never going to be negative. If it gets negative, this exponential function here does some wacky stuff and it gets real complicated. But if it's decaying, then your b is less than 1. Your multiplier is less than 1, which makes sense. If you're multiplying something by something that's smaller than 1 multiple times, it's going to get smaller and smaller and smaller and smaller. And so we could track out a couple key points here. So when x is 1, this point on our graph is going to be, you look at a times b to the first, a times b to the first, or just a times b. So this is 1 comma AB. 2, this point, is 2 comma A times B squared. Remember, B is squared first, the multiplier squared first, and then multiply that by the starting value, the y-intercept of A. And on here, we can do the same thing. So at 1, we've got a point here that's smaller than A. It's a lower height than A, but it's still 1 comma A times B. At 2, we've got 2 comma A B squared. So that's basically it. We have A is our y-intercept, or 0 is the y-coordinate of the y-intercept, and B is the multiplier. The thing that's taken to a power is our multiplier. Let's talk about how we might use this in a problem. Say we have a problem where we start with $2,000 and invest it in some crazy scheme that gives you a stupid amount of gain at a growth rate of, say, 20%. That's crazy. Well, let's write a model for this. Write the exponential function or equation. I use the word function, equation, and model somewhat interchangeably here. Write the exponential function for this, basically. Well, our starting value, our A, is 2,000. It's 2,000. And our multiplier is 1 plus the 20%, or 1.2. And so our function is y equals 2,000 times 1.2 to the x. Now, if we wanted to use this for something, how much will we have after, I don't know, say 6 years? Say it's 20% per year. How much after 6 years? Well, you just plug it in. Y equals 2,000 times 1.2 to the 6th, 5,971 and 97 cents. That's how you want to use it. Now, what if I wanted to go the other direction and ask, well, how long for it to double? For the investment to double. Oops. Well, you can plug it in. Well, to double your investment, you would have to get to 4,000. So y would be 4,000. You just plug in what you know. 4,000 equals 2,000 times 1.2 to the x. And so I could divide both sides by 2,000 just to make things a little bit simpler. Then we can kind of see what we're looking at here. And you'll see that it doesn't really matter what the initial value is. The goal is, at what point does 1.2 to the x become 2, become twice, become an overall multiplier of 2? Well, unfortunately, to solve this, you need a thing called logarithms. So for now, you're probably just going to have to trial and error this. So we'll just try a few things. Just try 1.2 to the, let's try 1.2 to the 3, I guess. You could start there. Just 1.728. Let me verify that. 1.2 to the 3. 1.728. So not quite 2. So let's try 1.2 to the 4th. That is 2.0736. So somewhere between 3 and 4 is the number that we require for it to double. Now, if we're rounding to the nearest year, I guess I would, to guarantee that my investment doubles, I would probably round it to 4 years, because you know at 4 years it will be double. It will be at least doubled. So, but if I wanted to get a more exact answer, well, it's going to be between 3 and 4, a little bit closer to the 4. So I might try 1.2 to the 3.6, maybe. And that will give you, and again, 3.6 is 36 tenths. That means you would take 1.2 to the 36 and then take the 10th root of that. So it does translate to a fractional exponent, which we do understand how that works, or we've seen it before anyway. But that's neither here nor there. 1.2 to the 3.6, you can kind of trust your calculator on this. It's 1.927, pretty darn close to 2. Well, let's try 1.2 to the 3.8. That's 1.999 and something. That's pretty darn close. That's probably as close as we're going to get. So probably I would say x is going to be around 3.8 in order for us to get double our money back. Now, the actual answer, if you do use logarithms, is which basically turns an exponential equation that we have to solve, it turns it into a linear equation, which we totally know how to solve. This is 3.8018. I'd love to talk about logarithms, but that would be a whole other video, I think. But anyway, trial and error gets us pretty darn close. And there's another quick and dirty way to get the doubling time. There's a little trick that some people use. If you want, and this just works for doubling time, not for other things, but if you want the doubling time, just take the number 72 and divide it by the growth rate. Called the rule of 72. Now this is totally an approximation. So in this case it'd be 72. Our growth rate was 20%. Now we use growth rate not even as a decimal, just as a percent. So we just take 72 divided by 20 and we get 0.6. So not bad, not a bad approximation. It's not perfect, but so another example, say your growth rate was 6%. Then you could say the time to double is about 72 divided by 6, or 12 years. So we're going to be doing these kinds of equations using trial and error. All right, so the next thing, let's talk about writing these equations. Writing exponential equations, constructing them from information that's given to us. Writing exponential equations or functions. I may not have enough room here. So you may not need to use all of these, but for the sake of completeness, I'm going to kind of give you all the possible situations. Now, for some of these situations, it's made a lot easier if you just know logarithms. But I'm going to show you how to construct these equations without using the logarithm function. So first situation is like we had before, where you're given the y-intercept and multiplier. If you're given those two things, guess what? You can just write it out. If the y-intercept is you're given a and the multiplier is b, you just write it out. Y equals ab to the x. You just plug them in. So slight variation of this, and I'll just kind of use them interchangeably, is if you're given the y-intercept and the growth rate or decay rate, because they might not tell you what the multiplier is specifically, but they might tell you the growth or decay rate. And in this situation, you would just have to convert your growth or decay rate to the multiplier before you plug it into the y equals ab to the x. Second type, we're given the multiplier and a point. A point on the function, or on the curve. It's not a straight line anymore, so we call it a curve. And the third case is we're not even given the multiplier. We're just given 2 points on the curve. Now, just like 2 points determine a line, 2 points determine an exponential function as well. So, say we're given the y-intercept and the multiplier. The extra possible variation of maybe we're not given the multiplier directly, but we're given the growth or decay rate. Here's our example. Find the equation Find the exponential equation with a y-intercept of 3 and a multiplier of 2.4. So a 1.4 growth rate is 1.4, or 140% growth rate. Well, you just plug it in. Let's do that. Y equals the 3 is our y-intercept, our A, and our multiplier is 2.4, which will be taken to the variable of to the input variable. And that's it. That's all there is to it. Well, let's say we're given the y-intercept and a growth decay rate. So let's say we've already done one with a growth rate, I think, with the 20% from the previous problem. So let's say we have the y-intercept and the growth or decay rate. So here's our example. Let's say our decay rate is 13%. And it goes through the y-intercept of 0, 6, say. So again, decaying, that means it's starting over here high and it goes low to this long tail thing. And this point right here is 0, 6. Well, here our decay rate means our multiplier is 1 minus that, or 87%, or 0.87. So now that we have that, we have our equation. Y equals 6 times 0.87 to the x. And that's it. What happens, we're going to get a little bit more complicated here, but it can be done with the tools that we have. Let's say we're given the multiplier or growth decay rate, and just not the y-intercept, and a point, some point on the curve. Well, okay, so let's find the equation. The exponential equation for a growth rate of 20%, a growth of 20%, and the curve goes through this point, 1, 9.6. Now, since it's going through a point that starts with a nice whole number on the x, that makes it easier. You can almost kind of trial and error it, but I'll show you kind of how we do that. So let's look at a table here. The growth rate, first of all, growth rate, that will tell us that our multiplier is 1.2. So now let's make a table here. Let's say here's our x and here's our y, and then we can kind of see what's happening here. Let's start with 0, 1, 2, 3, etc. It goes through 1, 9.6. Now to get to what happens at x equal 2, we would just multiply by what? By 1.2. 11.52, right? And if we want to do it again, if we multiply by 1.2 again, we get 13.824. So we've effectively multiplied 9.6 by 1.2 squared. But we're not really interested in that. What we want to know is, can we reverse engineer to figure out what's happening when x is 0? Well, if we multiply by 1.2 to go this way, well, to go backwards, let's divide 9.6 by 1.2. So let's do that. So let's take 9.6 divided by 1.2. Should be pretty nice. Oh, it's very nice, 8. Okay, well that means our y-intercept is 0, 8. Here's our y-intercept, 0, 8. In other words, A is 8. b is 1.2. I guess we're good to go. Y equals 8 times 1.2 to the x. And there it is. Now, if the point we were going through was not a nice one where we could just step back dividing by 1.2, it gets a little bit trickier. If they gave us 13.824 instead at x equals 3, well, we'd have to divide by 1.2 3 times, or 1.2 cubed. And so how far away we are, how far this y value is from the y-intercept is a factor. You have to divide it by a certain power of 1.2 of your multiplier, your b value. And so that means that power you divide by, the power of 1.2 you divide by, is determined by this distance here, 3 minus 0, or 3. Let's just, for example, I'll show you 13.824, if we divide that by 1.2 to the third, you're going to get 8 again. So even if you're not starting at 1, you can figure this out. I guess I could say y over b to the x will give you a. This is if you know your multiplier. You don't have to memorize this formula, but I think it's easier just to make a little table. But after a while, you might find it easier to use the formula. But this y over b to the x equals 8. Guess where that comes from? That comes from our original equation. Y equals a times b to the x. If you divide both sides by b to the x, guess what? You get a is y over b to the x. So if you know y and you know x, you can get a. So let's look at the third situation. The third situation is probably the roughest. So let's just look at an example. You say you're just given 2 points on a line. 2 points, sorry, on the curve. And this is just for completeness that I'm doing this. You may not run across this kind of problem. I don't know. 2 points on the curve. So say we have. We're going to do it kind of like the linear equation, where first we use the 2 points to figure out what the multiplier is, and then we reduce this back to situation 2, where we have the multiplier and a point on the curve, and we could just do it basically just like we do number 2. So here's the example. Find the equation or function through 1, 6 and 4, 48. Well, let's look at our let's scroll this up a bit and let's look at our let's look at a table. So we got x and y again. So let's go, since the x's are nice whole numbers, we can just count up 0, 1, 2, 3, 4. That's all the farthest we need to go. We got 448 and 1, 6. Now, like in situation 2, if we knew our multiplier, we could just divide 6 by that multiplier and we'd get our y-intercept. But we're not there yet. We need to figure out what our multiplier is first. Well, if we think about how we get from 6 to 48, we're doing 3 multiplications. We're multiplying by b, we're multiplying by b, and then b, and then b. That's an overall multiplication of b to the third, whatever our multiplier is. It's 3 because, well, to go from 1 to 4, it's 3. So if it wasn't a nice stair step, you could just take your x values and subtract them, and that would be the power of b that you're dealing with. So let's make a little equation with this. Let's remember what our final equation that we're looking for. It's ab to the x. We need to find a and b, our starting value a and our multiplier b. Well, but let's make them a little intermediate equation. We know b to the third. We know 6 times b to the third equals 48. Correct? Take 6, multiply it by b 3 times. That's b to the third. And you'll get 48. Well, then let's solve for b to the third. Let's divide both sides by 6. And you get b to the third power is 48 divided by 6 is 8. Now, to solve this, you want to get rid of that power of 3. So what you do is you do the inverse function, which is the cube root. Just do that on both sides. That means those kill each other off. And you just get b equals the cube root of 8. Cube root of 8 is 2. So b is a nice number of 2. It won't always be nice, but in this case it is. And you can test that. Multiply 6 times 2, you get 12. Multiply that by 2, you get 24. Multiply that by 2, you get 48. So that works out. You can check. Now we can go backwards. Let's divide by 2. Well, that means our a value is 3. So a is 6 divided by 2, or 3. So now we're ready to go. We're ready to write our equation. Y equals a, which is 3, times b, which is our 2, to the x. That's how I'll write it. You could write it as 3 times 2 to the x. Order of operations, that's still correct. But anyway, that's all I have for now. I'll see you next time.